So, good morning, good afternoon, good evening, everybody. Welcome to this week's seminar. Our speaker today is Paula Rulff, and she will talk about technical insights into advanced numerical methods applied in 3D EM modeling. Before we get to her talk, the usual intro, some overview of what's happening and how you can get to the other EMinars. So, many of you, sorry, I have some technical difficulty here because it's not showing me the slides in the right order. Now better. So many of you will know the MTNet page that has the list of all the EMinars, past and present. We are now our third year, so there are actually several pages by now. And if you look at the page for 2022-2023, you can see either the YouTube link or the link to the presentation for the previous seminars where speakers have made those available, and that's for the majority of them. Or you will see a registration link to register for upcoming seminars, EMinars. We have more speakers coming up this month. So next week we'll have Paulo della Avasana, and he will talk about a hot topic at the moment, using ChatGPT-3 for geosciences. So the sort of AI bot that has been making the news quite a lot. So I think that's going to be very interesting. Then Anna Platz from GFZ will talk about insights into different processing. Sorry, I have to move my screen. Processing strategies using magnetotelluric data from West Bohemia. So a noisy area in sort of southeastern Germany and the Czech Republic. So state-of-the-art processing techniques. Then Bruce McManus on UTEM, its origin, history, development, and discovery. So a different electromagnetic technique on the 22nd of March. And then finally this month on the 29th, Graham Hill, from Salt Lake City to the roof at the bottom of the world, the works of Phil Wanamaker. As many of you know, Phil died recently, very suddenly, and he's going to talk about Phil's scientific legacy. So, as I said, today it will be Paula talking about EM modeling and numerical methods. And Paula is a current PhD student at Uppsala University in Sweden. She did her MSc at the University of Potsdam and also worked at GFZ in the maintenance, among other things, of the MT reference station. So as some of you know, there's a permanent reference station in northeastern Germany that is run by GFZ. So if you are doing MT measurements in Germany, you can use that. And Paula was involved in maintaining that. And as part of her PhD project now in Sweden, she is developing a modeling and inversion code for 3D controls, 3D control source electromagnetic data. So with that, I will stop and hand it over to you, Paula.
Yeah, thank you. So, hope you can see my screen and my pointer now.
Yes.
Good. So thanks a lot for the introduction. I am honored to be here today to present this EMinar entitled Technical Insights into Advanced Numerical Methods Applied in 3D Electromagnetic Modeling. And the content that I will present in this EMinar is the current work of myself and two of my colleagues at Uppsala University, Laura and Michael. And I will give the presentation first, but Laura and Michael will both be available to answer your questions afterwards. So let's start with a short introduction. In the presentation title, it says EM modeling. In fact, we are focusing on frequency domain land-based magnetotellurics and control source electromagnetics. In both methods, we measure the electromagnetic fields at the Earth's surface, and the measured fields are sensitive to the electrical properties of the subsurface, which are mainly the electrical resistivity, but also the magnetic permeability, and then for high frequencies, the electric permittivity. However, the methods, they are differing in the origins of the electromagnetic sources. The magnetotelluric, the MT method, uses natural sources. The solar-wind magnetosphere interaction gives varying magnetospheric currents in a frequency range up to 1 Hertz. And the audio magnetotelluric frequency band originates from the global distribution of lightning discharges, while the fields propagate in the lossy waveguide between the Earth's surface and the ionosphere. For the AMT method, we talk about an approximate frequency range between 1 Hertz to 10 kilohertz. Controlled source electromagnetics, CSEM, on the other hand, uses artificial sources, such as electric dipole sources or loop sources. Regarding the modeling of the electromagnetic fields in both methods, the main difference lies in the implementation of the source terms. So for MT or AMT modeling, we can safely assume that we have the sources in the far field and we are dealing with plane waves. Thus, the source has to be impressed at the domain boundaries or at the anomalies, depending on the approach we are using. And in controlled source electromagnetics, we include the source into the modeling domain at a certain location and with a certain extent in source moment. In our modeling code, we use the so-called total field formulation in terms of the electric field for MT and for CSEM modeling. By having a closer look at both boundary value problems for both methods, we can see that they differ only in the representation or in the description of the source terms. In magnetotellurics, we include the source as prescribed fields or as a prescribed field at the domain boundaries in the boundary conditions. In CSEM, we directly include a source current in the right-hand side of the equation. To obtain solutions for two perpendicular source orientations, for example, if one wants to calculate or to obtain impedance tensors, the MT electric field formulation has its equivalent formulation in terms of the magnetic field. And in CSEM, the same equation, as stated here, has to be solved, but the source for the second polarization would then be oriented perpendicular to the first one, but still described in the right-hand side vector of the equation. Electromagnetic forward modeling describes the procedure of computing electric and magnetic fields at a number of receiver locations for a known measurement setup and a subsurface model. It starts with formulating the boundary value problem of your method and with deciding on a suitable discretization approach for solving this boundary value problem numerically. Then we have to discretize our modeling domain in a manner that we can compute accurate forward responses, assemble a linear system of equations, and apply appropriate boundary conditions. Afterwards, the system of equations has to be solved, and the solution can then be used to finally obtain the electromagnetic fields at Cartesian coordinates or in the coordinate system you want to at the receiver locations. The presentation title states that I will talk about advanced numerical methods. In fact, I will focus on advancing standard approaches for discretization, solving this system of equation, and boundary methods during this forward modeling procedure. But why are we actually working on this? Well, if we improve the mesh on which the forward responses are calculated and we improve our prescription of boundary conditions, we aim to obtain better accuracy of our forward responses, which means reducing the modeling error and the discretization error, and at the same time, reducing the problem sizes, thus the computational load per forward solution, which is also the goal for advancing the standard method of direct solvers, which I will talk about later, to reduce the computational cost per forward solution while assuring the accuracy of the solution. So don't increase the solver error. To then, in the end, speed up the inversion process. Because in an inversion, synthetic data have to be calculated in each iteration, and forward problems have to be solved not only for calculating the forward responses itself, but often also for obtaining the sensitivities or gradients. Thus, the faster one forward calculation is, the faster an inversion procedure, which gains nowadays even more importance when we want to evaluate our data in 3 dimensions. So here are the topics that I'm going to cover, which is discretization, boundary methods, and solving. And I will start right away with the discretization approaches. So discretization methods subdivide a computational domain into very small but finite-sized elements of geometrically simple shapes. The collection of all these simple shapes constitutes a so-called mesh. And the next step is then to take a system of field equations mathematically represented by partial differential equations that describe the physics you are interested in and formulate these equations for each of the elements. This is handled by approximating the fields within each element as a simple function. Very common are linear functions or quadratic polynomials, which with then a finite number of degrees of freedom. This gives an approximate local description of the physics by a set of equations, so our system of equations. There exist several numerical methods for discrete approximations. Every method has its strengths and its weaknesses. And in our forward modeling codes that we developed here and are working with, we use the finite-element method, and which is quite common method in electromagnetics, and then also the spectral element method. We will deal with triangular or tetrahedral shapes for the finite-element method, and hexahedral elements for the spectral element method. The CSEM forward modeling code is using finite elements and tetrahedral meshes combined with first-order edge-based interpolation functions. So we're modeling the total electric field in 3 dimensions. This is a quite common procedure. However, using lowest order interpolation functions, it can be actually quite difficult to obtain forward responses of good quality. To achieve really accurate forward responses, one has to either discretize the model domain globally very fine or use higher order interpolation functions. And both approaches can result in large problem sizes and computational costs. And another option is to implement goal-oriented mesh refinement, meaning that one designs a relatively coarse input mesh and an automatic refinement procedure then modifies the input mesh adaptively in these areas which have to be discretized with smaller elements to achieve better solution accuracy at the receiver sites, because that's where we are actually interested in the accurate field calculation. And such a mesh refinement is implemented in the 3D forward modeling code. But what does refinement actually mean? So it means that we have to calculate some error estimators for each element in our domain and identify the elements which have the highest error estimators. In each refinement step, these elements are then bisected if they exceed a certain threshold. We have implemented a goal-oriented adaptive refinement option, which can be combined with a uniform mesh quality improvement. The goal-oriented refinement is based on error estimators for a primal and an adjoint problem, similar to as presented by Shengyong Ren for 3D MT modeling, for example, in this paper. Our error estimators consist of 3 components. So this is the elemental error estimators. They consist of 3 components, which are residuals, then phase jumps in normal current density, and phase jumps in the tangential magnetic field. And which of those components shall be included in the error estimation is then customizable and can be defined by the user depending on the input model. So what are these phase jumps? When we look at 2 adjacent elements sharing one phase, there are some numerical continuity conditions which are fulfilled in the edge-based finite element formulation that we are using. For example, the electric field along the edges is ensured to be continuous, but some are actually not. which are, for example, the continuity of the normal component of the current density, illustrated here, and the continuity of the tangential component of the magnetic field across a common interface, which cannot be ensured in this formulation. And because of this, errors can arise, and the so-called phase jumps in both components are used as optional terms in the error estimator guiding the mesh refinement, as I said before. The CSEM refinement, which we have implemented, has some special features, which are, for example, that we can include these tangential magnetic field phase jumps, which can be helpful, or we tested that this is helpful for models with magnetic permeability contrasts. Then there is a refinement on a low quality mesh option, where one can increase the mesh quality only in the last refinement step or the last refinement steps, which saves actually quite a lot of time and memory. And we can use an average global error estimator and an average error estimator at the receiver sites, which only takes into account the elements where actually receiver sites are included, to assess the refinement behavior. Furthermore, we noticed that we cannot conduct error estimation for goal-oriented refinement in the same way as for the magnetotelluric problem, because, coming back to the sources, the error estimation is dependent on the primal, but then also on the primal is of actually physical source, but then also on a dual source term, because we have to also formulate a dual problem for this error estimation, which, as we said before, differs between the far-field MT modeling and the CSEM modeling. Thus, the source strengths in the adjoint problem take the distance to the primal source, which is indicated by R here, into account, and this ensures that all receiver locations are included equally in the error estimation. And then the element error estimators are also weighted with the local field strength, which avoids amplitude-dependent over-refining of the mesh. So we had did some checkups, and for both of these weighting factors, the refinement actually worked quite well. To demonstrate how these element error estimators guide the mesh refinement, we tested a bunch of synthetic models. And I thought now we look at the model with a receiver line, a source in the middle, and two different anomalous blocks below the receiver line. And here we see the element error estimators of the initial mesh to the left, and after refinement with error estimator RJ, meaning that we use residuals and phase jumps in normal current density for error estimation. And this is around the conductive 3D anomaly of the model. And when we look at the meshes, we see that not only the mesh is refined, so the elements are smaller actually in the refined mesh, but also the element error estimators decrease during the refinement procedure around the anomaly. And it's very hard to see, but they also decrease around the receiver site here sites here on top. Also, the global and the receiver error estimators decrease, while the degrees of freedom, so the problem sizes, increase as elements are added to the mesh. And here we see that we used a refinement on a low quality mesh option, and then a last refinement step where we also increased mesh quality. So that basically means that we add a strong global refinement as well to the refinement procedure to achieve the accuracy which is in the end actually needed. However, the most important point is that with the suitable automatic refinement, which we identified as, for example, here the blue crosses or the squares, we design a better mesh to obtain more accurate forward responses than when using a globally fine but memory demanding mesh, which is basically this orange point here. We don't apply refinement, but a really, really good quality factor of the mesh. When applying refinement or this refinement method to more complicated models, it can, however, be less straightforward to achieve a reasonable refinement behavior. We considered an ore deposit model where mineral deposits of different shapes, different resistivities, and magnetic permeabilities are included in a resistive half space. And then we calculate the forward responses over a quite wide frequency range. As we include the mineral deposits in accurate shapes, we mix really, really tiny elements in the deposits with very large elements elsewhere in the model region. So that means the starting problem size was already quite large, and we observed that we have to prescribe volume constraints in the complex shaped anomalies to actually not get too tiny elements in there. And then a mesh refinement procedure with additionally mesh quality improvement at each refinement step led to the desired result, that the mesh was improved not only at the resistivity contrast, but in the end. So to the left here, we see the initial mesh and then the refined mesh. So the mesh was refined at the anomaly again, then around the anomaly, but also at the receiver sites and at the source indicated in red here. And we obtained really good forward responses. In another project, we were trying to answer the question, how do we discretize and refine our model when metallic infrastructure, such as metallic cased wells, are included in controlled source electromagnetic setups? So metallic cased wells are often present in exploration settings. They have to be taken into account when modeling the electromagnetic fields, as they are highly conductive. It is really challenging to discretize them because of the large scale differences. So you have thin, long welds compared to geological formations. And we are aware that several methods have been proposed already to wisely model steel-cased welds. But in this work, we are focusing on the presentation of a steel-cased well as a perfect electric conductor, in short, PC. And it was shown in those publications that a metallic cased well can be either represented by a replacement prism, or when the well is close to the source, also by a combination of prism and perfect electric conductor, or when the source is sufficiently far away, it can also be represented by a PEC only, so a perfectly electric conductor only representation. And this PEC is implemented like a boundary condition on the mesh edges. It reduces the problem sizes drastically, as no tiny elements are needed to discretize a few centimeter thick prism, and meshes can be constructed such that an arbitrary orientation of the wells is also possible. We consider a model containing basin topography, a receiver line, an inline horizontal electric dipole source, and a metallic well, which is 560 meters apart from the source and only 200 meters deep. We applied two forward modeling codes, so MyCode and PECGAM, for this work, which are based on quite commonly applied concepts. However, as I said before, the Alpha 3D code has the special feature of goal-oriented mesh refinement, and PECGAM supports higher order basis functions, which are the both methods which we combined and also applied to tackle the question of wisely discretizing a model with steel-cased wells. We investigated that for such a shallow well distant to the source, a PEC-only representation of the well is sufficient. And by looking at the element volumes of the refined mesh at the borehole location, so here we actually have the borehole location up to 200 meter depth, which is represented by a PEC only, we can see that the goal-oriented refinement refined this PEC a lot in the upper part, a bit in the middle part, and not at all in the lower part. When we look at the inline electric field responses, the electric field is strongest at the source, which is here, and then it has a discontinuity at the well location. The normalized differences to the reference solution near the well are here for the initial mesh and here for the refined mesh. And when we look at the scale, we see that those for P1 elements, there's just the crosses, they improve from about 10% at the well to about 2%. We can thus conclude that the goal-oriented refinement can handle these form of modeling wells with perfect electric conductors quite well. However, to go a bit into more detail, for this model, a solution with an average normalized difference below 2% for inline, which we see here, And cross-line responses can just be achieved by using from the beginning quite fine source and receiver elements, and then the goal-oriented refinement, but also higher order P2 elements, which are the circles I put here below the yellow triangles. So this is the first point is always the P1 solution, and we have P2 solutions and P3 solutions, so higher order elements run with the PETCAM code. This results in higher runtime, but medium memory consumption. And the most important point is that we could not achieve the same accuracy with the globally fine high quality measures, which are the green markers here, which demonstrates that effectiveness again of the refinement method. To conclude with the refinement. For controlled source electromagnetics, we are not only working with finite element measures, but also with the spectral element method, which is rarely used, but quite powerful. The spectral element method combines the flexibility of the finite element method with the high accuracy and favorable convergence properties of the spectral method. So hence the name, the spectral method. And the underlying mathematical framework shares many similarities with the finite element method, but it differs mainly in the choice of the basis functions and the corresponding quadrature scheme and points used. The code developed here at Uppsala University by my colleague Michael employs mixed order Kerr-conforming basis function, given by this expression below here, and defined on hexaedral elements. The basis functions are built using Lagrange polynomials defined on Gauss and Gauss-Lobato-Lagrange quadrature points. And the code's main features include variable physical properties, then arbitrary high-order basis functions, and a solver which can either be a direct solver or a preconditioned iterative solver, which I will talk about later. Here you see an example where we compared the spectral element approach with a finite element code. The model consists of a layered Earth with a buried body that could represent an ore body, for example, and the source is a 400-meter long grounded cable offset by 500 meters and perpendicular to the 4-kilometer long receiver line, with receiver spacings of 400 meters spanning from -4 to 0 kilometers. And transmitting at a frequency of 100 Hertz. Both the finite and the spectral element code employ a second-order approximation. And here we see the comparison of the forward responses, showing actually quite good agreement with the reference solution, which was obtained with custom for the X component of the electric and the X component of the magnetic fields. You see the real and the imaginary parts plotted here. And in the table, you can see the computational quantities between the two simulations, which is the number of elements, the number of degrees of freedom, and the computational time for the spectral element code and for the custom code. And one can see that the degrees of freedom are kept about the same, and hence the overall simulation time of both algorithms is also about the same order of magnitude. But in terms of elements used, the spectral element method requires about half as much elements as the finite element code, but as shown before, results in the same accuracy. So the keyword accuracy brings us then to our next topic, the boundary methods. Why do we need them, and why do we have to set boundary conditions for our modeling domain? Well, because it's not infinite. We cannot simulate our local electromagnetic fields, which are continuously traveling through the Earth as a whole, because it's just too large, and we have to define the sources somewhere. Thus, we have to prescribe certain field values, so-called boundary conditions, at the borders of our small 3D modeling domain. When modeling, the boundary condition should ideally absorb all outward directed fields. Otherwise, so-called boundary effects will occur. And these boundary effects can be understood as reflections of the outward directed fields at the boundary and they are unphysical. Thus, the calculated electromagnetic field will then be wrong. A standard approach is to use Dirichlet boundary conditions, which means that the field values that are prescribed at the boundary must exactly match the solution that would be computed there if the boundary wasn't there. And now, in these examples, we are considering magnetotelluric 2D modeling. The empty source is far outside the modeling domain, and depending on the modeling approach, the source is represented either at the anomalies or at the outer boundary. In the total field approach that we use here, the source field is represented at the outer boundary. So the Dirichlet boundary conditions should do both, impress the source field and absorb the outgoing field parts. So typically, to calculate the field as exactly as possible, the analytic 1D solution to the background of the model is calculated and then prescribed. The lower boundary is placed so deep that the electromagnetic fields decay to zero, and the outer boundaries are placed far away from any 2D anomaly, so that the anomalous field decay then towards the boundary, and that boundary effects are minimal. But there you need quite large domains, and this leads to a large number of unknowns, so large problem sizes, if the modeling measures dense, for example, also in the air for high frequencies. However, this approach works well if the background of the model is indeed a 1D horizontally layered model. If the background is not 1D, as it's the case for many realistic settings, for example, at ocean-continent contrasts or dipping layers or topography changes between the left and the right, the 1D section at the left and the 1D section at the right is different. One common approach in such a case is to apply the correct solution to the left and to the right section at each side, and then interpolate between the two solutions along the top boundary. The problem here is that the interpolation is only an approximation. If the background does not change according to the interpolation, boundary effects will occur at the top, and they can affect the solution in the entire domain, also at the receiver side. And in such a case, the solution at the receivers is not as accurate as one would desire, because it's affected by the boundary condition, and it is actually unknown how large the effect of the boundary conditions is on the solution. As an alternative to Dirichlet boundary conditions, we apply perfectly matched layers. This is a method where one adds a sequence of damping layers at the boundary. In these layers, the field is damped to zero in a reflection-free manner. At the outer end of the PML, which is here, zero Dirichlet boundary conditions are then applied. This means that you do not need to know the solution at the boundary, opposed to Dirichlet boundary conditions, where the solution at the boundary has to be prescribed exactly as possible. This damping is governed by a damping coefficient, which depends on the distance to the PML. So this is the damping coefficient here. This is the distance to the PML, and which increases exponentially. So this exponent beta is usually chosen to be 2 or 3. And then a general scaling factor alpha. We see in the upper plot here on how the damping exponent grows with each layer. And in the lower plot, we see how the electromagnetic field is then damped accordingly. The real and imaginary part are plotted for a frequency range of 10 Hertz. When these parameters are chosen carefully, the PML become perfectly absorbing within the machine accuracy. So since perfectly matched layers are absorbing to field parts of any frequency and any incident angle, no boundary effects occur. And consequently, the boundaries can be moved much closer to the anomalies without disturbing the solution at the receiver sites. Since perfectly matched layers damp the solution to zero, they can directly replace homogeneous Dirichlet boundary conditions in the anomalous field approach. But applying PML to the anomalous field approach is limited to cases with a 1D background. To replace inhomogeneous Dirichlet boundary conditions by PMLs, we implement a numerical method called total and scattered field decomposition, in short, TSFD. And this method was originally developed for antenna applications where the scatterer is completely surrounded by free space. But in geophysics, the Earth occupies half of the modeling domain and the boundaries. So we adapted the TSFD approach for such cases, which I'm going to show now. We developed two different setups for two different types of models. The first case is the horizontal TSFD. The modeling domain is divided along a horizontal interface, which is the red line here. And in the region below, the solution is computed in terms of the total field values, and the incident field is impressed at the interfaces around this region, so the outer boundaries, and at the TSFD interface, which is here. The upper region contains only air. Here we solve in terms of the scattered field part, which is the response of the Earth to the incident field. This field is then damped completely by PMLs in the upper part, which are applied here at the top. That way, the interpolation between the left and the right side is avoided, and this method is useful for setups where the model differs between the left and the right boundary, as for example in this model I display here. Then the second setup contains a surrounding TSFD. This setup divides the domain along a rectangular interface into a total field region and a scattered field region, comprising the area of interest. So the total field region comprising the area of interest and the scattered field region. The scattered field region contains only the background of the model and the interface. The normal field is impressed at the incident field to the inner region. The anomalous field generated at the 2D structures is then solved for in the outer area, which is here, and damped to zero around by the PMA at all outer boundaries. And this setup can only be used for models with a 1D background, but it allows to move the outer boundaries very close to anomalies and receivers. And this shrinks the entire modeling domain and can therefore reduce the number of unknowns, especially when the modeling mesh is really dense. For example, when you model for high frequencies. How is this concept implemented in the numerical approximations? So the modeling domain contains two regions, the total field region, T of R, and the scattered field region, S of R, in which the solution is computed in terms of a different solution variable indeed. And the difference between the two variables, the total and scattered or total and anomalous, is the field, which is impressed at the TSFD interface. So this means that there's a jump in the solution exactly at this interface. When we look at this TSFD interface, how it would look in a mesh, then we see that the nodes at the TSFD interface, we define them as total field nodes. The scattered field region elements touching the TSFD interface have corner nodes in both regions and must incorporate this jump between the two fields. This is achieved by adding the appropriate field jump to the nodes at this TSFD interface and by subtracting it from the scattered field region node, from the scattered field region nodes, which are adjacent to the TSFD interface. So this is basically the equation here, that we have the right-hand side vector and the system matrix, and U would either be the electric or magnetic field which we are solving for. So the general concept of applying TSFDs and PMLs to magnetotelluric modeling is in the testing stage right now. And Laura's paper is under review, so I'm not going to show results now, but as a spoiler, the results look quite promising and fulfill the aim of keeping the accuracy of the forward responses while shrinking the modeling domain, and thus decreasing the computational cost per forward solution. So now I'm already coming to our last topic, which is solution methods. Linear systems of equations can be solved using either direct or iterative solvers. There exist some key differences between direct and iterative solution methods in terms of robustness and ease of use, then time and memory requirements, and also scalability capabilities. Direct solvers are very robust and easy to use, but they require a lot of memory and do not scale optimally. So thus one has to use computer clusters to solve really large problems. Iterative solvers, on the other hand, are less robust than direct solvers, but they need less memory capacities. To ensure robustness and improve convergence rate, preconditioning has to be applied for iterative solvers. Computer clusters might not always be accessible to anyone, so direct solvers are not necessarily the optimal solution. But with proper preconditioning, on the other hand, iterative methods should make large-scale problems accessible on moderate computer platforms. Thus, iterative solution methods are very promising, and I will describe now in the following the one that was implemented for the spectral element CSCM code here at Uppsala University. So to start off, there are some prerequisites for solving a system of equations iteratively. If the system of equations is not set up as a real equivalent formulation of the complex valued formulation, which means that we transform our complex system into a real equivalent system, one needs to transform this complex valued system. So this is the transformation, and now we have a general system of equations. One could also state like this, for which a very robust and efficient preconditioner, which we are going to need, is actually known. It's called PRESB, and looks as shown here. Given that this block A is symmetric positive definite, and in this case, all the eigenvalues will lie within 0.5, within this interval between 0.5 or 1, which means that the iterative solver will converge very quickly. And in addition, PRESB is known to be independent of discretization and material parameters, which is very beneficial for our problem. So we can see that our system fits the general block system for which PRESB is an excellent preconditioner. And hence we solve our system with the generalized conjugate residual algorithm, which is an iterative algorithm, preconditioned with this preconditioner called PRESB. Applying PRESB corresponds to solving system of the following type and is done by performing these steps outlined here in the algorithm. And we don't have to go into detail, but the interesting thing is that it involves solving two systems with this matrix H, and then some additional vector operations and one vector matrix multiplication. This algorithm, the algorithm 2, shows the generalized conjugate residual algorithms and details on how this preconditioner PRESB is used within the procedure. And the interesting point here is that the overall solution method is of outer and inner time, meaning that we have an outer iteration solver or an outer iterative solver, which is basically this loop here, in which inner systems require solving, which is called here at this step 4, that we call the algorithm 1, the inner solver within the outer solver. So we have an inner-outer algorithm. Details on the iterative framework. The whole iterative framework is written in modern Fortran using MPI parallelization, and it relies on libraries such as PETSI, MUMS, and Hyper. And as said, the solution method is of outer-inner type, where the outer algorithm is the generalized conjugate residual method, which is preconditioned with PRESB, and the inner systems are solved using either direct solvers. So the inner system can be solved either directly, there we use the MUMS solver, or iteratively using GCR or FGMREF preconditioned with the multigrid-based EMS solver, which are quite commonly applied and available iterative solving approaches. And now we tested the iterative framework, of course, and here we show the two models which we use to test this framework. One is a simple layered Earth model, and the other one is also a layered model, but with a buried 3D anomaly. And here are some model information. And the most important thing here is to note that we use first order approximations for the calculations, and the degrees of freedom are for the real value block system. So this means that they are actually twice as many as in the corresponding complex valued system. So this is the computer system, which is used to run the simulation, and the simulations will run on 2 MPI processors. Coming to the tests now. We tested if the framework is robust with regard to frequency. So here you see the convergence curves for different frequencies from 0.1 to 10,000 Hertz. And a convergence is reached really quickly in all of these cases. When we look at the same information in tabulated form, including simulation times and peak memory consumptions and the outer iteration count for all the frequencies, with the 2 methods for the inner solver using the iterative solver and then the direct solver. The key observations are that if the inner system is solved iteratively, which is done either here or there, we require way less time and way less memory than we use when we use a direct solver to perform the simulations. Except, in fact, for the highest frequency, which is indicated in red here, which means that the inner solver loses efficiency for very high frequencies. So we were checking this, and when we have a look at the convergence rate just for the inner solver for the different frequencies, we observe indeed that for the highest frequency, we require way more iterations than for all the lower ones, which explains the increase in time. And then again, then basically found out that it indicates that the preconditioner is not suited for frequencies which are 10,000 kilohertz or 10,000 hertz or louder. We also tested if this framework is robust with respect to or with regards to problem sizes. This table shows the robustness measures with respect to problem size. So these are the different problem sizes we tested across different frequencies for the layered Earth model. We see a stable outer iteration count with respect to problem size and a computational time increase, which is about linear. And we also tested the solver's robustness with regard to variable magnetic permeability. So the magnetic permeability in the ore body, so in the 3D model now, is varied from 1 to 10. And the simulations are run across these frequencies. We observe again that the outer iteration count, so now we have to look basically in this direction, and for one frequency, the outer iteration count remains stable, indicating that the solver is robust also with regard to magnetic permeability variations. So staying at the variations or the subsurface material property variations, we also tested and by adjusting the permittivity of the cover in the model and the background or host rock. And we performed at the same time runs where we also adjusted or changed the permeability of the buried ore body. And we run the simulations again for several frequencies and look at the outer iteration count and the time. And we can again observe that the outer iteration count remains quite stable. So to sum this iterative solution methods up, what's actually better? Is it direct solvers or iterative solvers? Again, a table. Here you see a comparison between solving the complex system directly with the MUMS solver and using the developed iterative solver. And note again that we have the inner system be solved either directly as well or everything iteratively preconditioned. And we can clearly see in terms of computational resources, the iterative solver using an inner iterative solver comes out on top and requires the least memory and time. Compared to that, the direct solver requires a lot of memory, which might easily become the limiting factor for larger systems, as observed for the larger system of 6 million unknowns that we tested in this round. So to sum up, this talk was aiming to give an overview of the numerical methods we implemented to advance 3D electromagnetic modeling, which is goal-oriented mesh refinement, spectral elements, advanced boundary conditions, and iterative solution methods. And if you're interested in more details, you can have a look at our papers. And then we would like to thank a bunch of people, which is our supervisors, and then the electromagnetic community for really good feedback at conferences, the reviewers of our articles and our funding resources, but then of course also MTNet and the great EMinar team. Thank you for inviting us, for giving this talk here today. And as I said before, I was presenting parts of this work on behalf of my colleagues. And they are with us now to answer some topic-related questions. So you see the topics here below our names. So please feel free to ask, and yeah, we will answer your questions according to the topics we are most experts in. Thanks a lot.
Yeah, thank you very much, Paula. That was very interesting. Now, everybody, please type your questions in the Q&A box, and I will read those out, and then, well, one of those three will answer them. Now, I have quite a few questions myself. I sort of ask maybe one or two while people are typing, and then I sort of leave it for the audience to ask more questions. So maybe start with one of the things you talked about last, this comparison about direct versus iterative solver. Now, I'm not a great expert in this, but it was always my impression that direct solvers have their biggest strengths when you need to solve the same system or similar systems with different right-hand sides many times. Yes, and because iterative solvers, you always start from scratch, and direct solvers, you do some sort of factorization, right? And I always thought the CSEM sort of case was something where these direct solvers would be quite beneficial. So can you comment on that? Is the like potential for reuse in this way you do it sort of limited, or did you have a small number of receivers and maybe with like hundreds of sources, the balance would be different?
Michael, would you comment on this?
Yeah, I guess this is a question for me. I mean, you're completely right that if you have multiple right-hand sides, then the direct solver will for sure come out on top. Although there are some strategies which I haven't looked into, but I've read about them, that help iterative solution to become competitive. The way I looked at it so far is mainly for modeling. So then there is in that sense only one source and not multiple sources. So for that case, it's pretty beneficial to use iterative solvers, and to make it viable for inversion, yeah, one has to find a good solution to deal with multiple right-hand sides. I think that's all I can say to answer your question.
Okay, and just to clarify, so this was because This was for a single CSEM source, and for example, if you had several CSEM sources, you would be able to reuse the solution of the direct solver, or was this already for many CSEM sources?
Yeah, it was for a single source.
Okay.
In case of the iterative one, yes, and the comparison was then done for a single one.
Okay.
Yeah.
Yeah. So at least potentially, if you would have a big survey with many sources, that balance could shift a bit.
Yeah. Yeah. For that, as I said, you would have to find. I mean, there are strategies that will help an iterative solution to work with multiple right-hand sides, so that you don't have to redo the whole iterative process, because it's dependent on the right-hand side, and so the residual will change. There are some strategies to do that, but I that's not implemented in my code yet.
Okay, yeah, thanks for that. Okay, we have some first questions coming in, so I'll keep sort of my other stuff in the background for you for now. So we have Longying Chow. Thank you for the talk, Paula. Have you compared the parallelization performance between direct and iterative solver? I think it's also about scaling, yes, so many processes and these things.
Yeah, I guess it's directed towards me again. We haven't had the time to look at scaling that much yet, so it's one of the things I would like to do in the future. But not from experience, from other papers, the preconditioner we use and this this multigrid based auxiliary space Maxwell solver scales extremely well. This has been shown in other papers. I can refer to a paper by Greiver in 2015, which shows this scaling of the AMS solver well. So one can hope that it should, in theory, it should scale as well for our method. So it should scale well, and then, I mean, usually it's kind of known that direct solvers at MUMS at some time can have, well, they will, if you use more and more processes, the ratio of synchronization and communication gets worse as you use more and more nodes per process.
Yeah. Yes, I think that's sort of a common thing. And so there's a second question also by Longying Chow. And have you compared different preconditioners?
Yes, in the second paper on the iterative methods, we compare our Presby preconditioner to a block diagonal preconditioner that uses a very similar framework. It uses a slightly different outer iterative solver, and it uses different inner iterative solver, but it uses the same preconditioner for the inner solver. And Presby is slightly better in terms of iteration number, and thus is slightly faster in its simulation times. In terms of memory, it's equal.
Okay, thanks. Okay, I have, as just a second, I have a chat message from Alan who has internet trouble. So one question from Alan is if you have any analytical solutions that you have compared your numerical ones to. I mean, you showed your comparison with other codes, but have you done sort of either analytical or semi-analytical comparisons as well?
maybe I can answer this question. So yes, we did for the simple models, for the layered models and for the homogeneous half space models, we used semi-analytical solutions to compare the 3D, the developed 3D forward modeling codes with. Yes.
Yeah, thanks. And we're still waiting for maybe a few more questions, so I'll chip in with another one, which sort of relates to, if you want, so the talk as a whole, like all three of you. So you have two different methods, yes, that you're working on. You have the finite elements and the spectral elements. And what was the reason to say, okay, we will actually have two codes instead of saying, okay, maybe I think you started with the finite elements. Yes, Paula, you were probably one of the earlier ones. And something doesn't work and we just try to fix it with the same method rather than, okay, now we try spectral elements as well.
Yeah, I think this question could be answered in several different ways, depending on who you are in this construct of colleagues here. So I was actually not the first one. Michael was the first one.
Okay.
But so in general, we have this inversion framework EMinar here at Uppsala University, which Thomas Kalter developed with a lot of co-authors. It's working for 1D and 2D problems. And the idea was to implement several different, so expand it with several different 3D approaches, not only for forward modeling, but also for inversion. And then we also know that regarding inversion, it's often good to calculate forward responses with a different code and a different meshing approach and to implement this. And there we are in the process. But I think this was the idea why we would actually do basically these parallel CSEM developments with the two different meshing and interpolation approaches. And then I think, well, Michael can maybe add, but I think this spectral element approach was actually just so interesting that they, continued working on this and developed this code because it's really, or not really used otherwise, but it's working quite well. Michael, if you want to add something.
Yeah, as you said, I started slightly before you, and at the very start, it was actually the idea that I would write a finite element code. And then we were on a conference and we were talking, we got to a point where we were talking about different discretization methods and different ways of using different polynomials to interpolate interpolation to do interpolation. And then someone mentioned Chebyshev polynomials, and then we started looking into that and found the spectral elements method, and then we decided to see if we can make it work for CSEM. So that's how how I started with the control with the spectral elements method.
Yeah, and I mean, it's probably not a fair question to ask, but where do you see the potential? Will you keep doing this? Will you sort of keep this sort of complete line of sort of parallel development on, or is there something where you're like, okay, this was neat, but maybe when we go to real big problems and so on, there is something that's a slight favorite at the moment, or something that has maybe a bit more of a future?
Maybe I can start. So for what we are going to do in the future depends a bit on what kind of jobs we will have in the future.
Yeah, of course.
But from the point now, what I think we can actually say is that meshing complex subsurface structures is easier with the finite element tetrahedral shapes. But then meshing with the hexaedral elements is actually more straightforward. So I think it depends a bit on the model and the application for which method I would go for. So I think it's actually good to have both codes available. Maybe Michael, if you want to add something.
No, I think you covered that well.
Yeah, and I mean, okay, we're still, there's still no other questions, so I'll just keep asking because it's sort of related to this. So is that a function more of the tetrahedral versus hexahedral? Because I think you can do both with either method, right? You can do spectral elements with both, and you can do finite elements with both. Or is it really spectral versus finite elements that sort of, you know, the condition numbers of the matrices and so are fundamentally different?
Michael, would you comment on this?
Yes, I can. Well, I can start with saying that using the spectral element method for tetrahedral elements is pretty tricky. It requires a lot of additional work to implement it, and I've only seen one paper that managed it to do for edge elements, so curl conforming elements. That's the tricky part, and they have to do a lot of conversions from the tetrahedral element to the hexahedral elements and then backwards to make it work.
Okay.
It's not as straightforward, because otherwise I think one could use the spectral element with the tetrahedral element, the spectral element method with the tetrahedral elements, which should be beneficial in terms of conversion rates, which by theory are better for the spectral element methods, because we inherit the properties from the spectral methods. Now I forgot what was the second part. The condition number. Yes. Yeah, I'm thinking which one is better. I'm not entirely sure. I think the condition number is a product of the elements and the distortion of the elements and the element order we use and the material parameters. So it's really difficult to say where exactly everything everything like goes well or not well.
Yeah, sure. And I mean, I just meant it more as an example
Yeah.
of one of the factors that influences things. So, but yeah, I see. I didn't know that it was so tricky with the spectral element method. Okay, I'll maybe ask one last question, and then if we don't have anything more from the chat, we'll conclude it, because there you also talked a bit about this sort of the boundary conditions, right? And this perfectly matched layer approach, which is something I don't think many people have done. And you talked a little bit about it. Okay, let's you reduce the size of the discretization domain in under certain circumstances. Yes. So do you see this as a promising method in practical application, or do you have to be very careful about, you know, the size of your domain, and at the end of the day then you end up with sort of relatively large domains anyway to just to make sure? Yes, I mean, have you tried it with, let's say, real data already? You're muted, Laura.
Yeah, I know. Now I'm unmuted. So we've tested it like for forward modeling only and not in inversion. So I think if you were to include it in inversion, it would be like more work, but I can't say anything about that. But yeah, so it really depends how many elements you can save. So obviously when you use unstructured meshes and you have very large domains, but you can have a relatively coarse discretization towards the edges, then maybe by adding these layers at the boundaries and moving them closer, you don't really gain something in terms of problem size. But then if you have a very densely discretized mesh, for example, at high frequencies, when the air layer has to be really dense, and still it has to be quite large. Then actually you can save a lot of unknowns by moving the boundaries much closer, even if you have to add a few unknowns in the PML. So you always have to look at the case you actually want to calculate, because the PML do add some unknowns because you add layers and they contain, well, elements. But at the same time, if you save more nodes than you add, then yeah, your problem becomes smaller.
Yeah, okay, and I see. So at the moment you use it for forward modeling. Of course, there you have some quite good control, and so you have to still test a little bit how it happens, like an inversion, right, where structures develop, and all of a sudden you get things that sort of move outwards towards the boundary of your mesh. How that then sort of will work. I mean, that I think will be quite interesting.
I mean, another point, except for the problem size, is also the accuracy of the solution. So if you have a quite realistic model, for example, where you have the ocean on one side and like topography and the continent on the other side, then there's no possibility to use directly boundary conditions and prescribe correct boundary conditions, because I mean, there is a change between the left and the right side, and whatever your interpolation is, it's not true to the whatever background you have or whatever you define to be the background. So if you apply this horizontal TSFD where you have PML at the top, you actually don't have to make any approximations or assumptions about how the field is behaving between the left and right side. So actually you can get rid of some artifacts which are due to the directly boundary conditions by using PML. So then you might add a few more unknowns, or maybe you can even go closer and then you don't really add a lot of unknowns, but you have a higher accuracy and you can be sure that your boundary conditions don't affect your solution in a way that, yeah, you don't want.
Yeah, and of course, I mean, that's actually a very good point and very interesting, because I suppose these sort of amphibious experiments are certainly something of interest in the future, and have been done already. Yes, where you go into the sea, but you also have measurements on land, and then you have exactly the situation you're talking about. And yes, or I know that a lot of codes are struggling with that for, well, a variety of reasons, and if you can eliminate one of those factors, I think that would be quite interesting. Well, I don't see any more questions in the chat, so I would like to thank, well, Paula, but also Laura and Michael for the presentation and answering questions. So next week we have Paula del Alvasada. So that's going to be interesting. And yeah, thank you very much for everyone, and have a good day.
Thank you.